So till now we have completed all the conformations of ethane, butane and cyclohexane, their energy diagram, their conformational analysis, how to draw the structures, how to do their analysis, how to calculate their energy, everything we have discussed. Now let us see the next part of our syllabus, that is determination of configuration of geometrical isomers. There are various methods available for the determination of configuration of geometrical isomers. The first method is physical method. Generally, the trans isomers have got higher melting point and lower boiling point as compared to the cis isomer. Okay, the second thing or second method by which we can separate or by which we can determine configuration of geometrical isomer is by measuring their solubility. Solubility of cis isomers is in general more. For example, solubility of malic acid is 3 gram per 100 ml of water at 293 degree Kelvin, and the solubility of fumaric acid, this fumaric acid and malic acid, they are considered as geometrical isomers. Okay, the solubility of fumaric acid is 0.7 gram in 100 ml of water at 293 degree Kelvin. Now, if we see the dipole moment, or if we compare the dipole moment of cis and trans isomers, we can see here in case of cis isomer, both the dipoles are pointing in the same direction, whereas in case of trans isomer, the dipoles, they are opposite to each other. They lie opposite to each other. So in case of cis isomer, we can find some value for the dipole moment, whereas in case of trans isomer, as because the dipoles, they oppose each other, the net dipole moment of the molecule becomes 0. Okay. So using dipole moment also, we can, or by measuring the dipole moment also, we can find out whether the isomer is a cis isomer or cis geometrical isomer or trans geometrical isomer. Here 2 examples are shown. The cis isomer is having 0.4 dipole moment, whereas here it is 0. Here we have to observe that in case of cis isomer, the dipoles, they lie or they are pointing in the same direction, whereas in the trans isomer, the dipoles, they oppose each other. Hence, the net dipole moment of the molecule becomes 0. Next, determination of configuration of geometrical isomers by method of cyclization. Cyclization of malic acid to malic anhydride can be done very easily, whereas fumaric acid does not give its anhydride upon heating that easily. Now, when we talk about malic acid, it is cis isomer, whereas fumaric acid, if we see here, it is a trans isomer. Similar groups, they are lying opposite. Hence, fumaric acid is trans isomer. When we heat this malic acid, these 2 COOH group, they interact in such a way that a anhydride bond is established. Here, one molecular water is liberated out. However, in case of fumaric acid, as because these COOH groups, they are lying opposite to each other, no anhydride formation will take place here upon heating. So by method of cyclization, also we can determine the, or we can find out the configuration of the geometrical isomers. The next method is by converting into compounds of known configuration. One of the 2 isomers is converted into a compound having known configuration. Here, what we do? By converting into compounds of known configuration. One of the 2 isomers is converted into a configuration or a compound having known configuration. Here we can see here trichloroprotonic acid is taken, which when subjected to hydrogenation, it will give crotonic acid. Okay. This trans trichloroprotonic acid upon hydrogenation gives trans protonic acid, whereas if we take cis trichloroprotonic acid, now if we see this structure of trichloroprotonic acid, here both the hydrogens, they are lying opposite, hence it is a trans isomer. When we talk about this structure here, both the hydrogens, they are lying on the same side, it is called cis trichloroprotonic acid. Trans trichloroprotonic acid, when subjected to hydrogenation, it gives protonic acid, to be specific trans protonic acid, whereas cis trichloroprotonic acid upon hydrogenation gives us cis isoprotonic acid. Clear? Likewise, trichloroprotonic acid, this is trans isomer, when it is subjected to hydrolysis, it gives fumaric acid, whereas cis trichloroprotonic acid upon hydrolysis, it does not give fumaric acid. So based on the conformation of the final product, also we can find out the orientation or the geometrical isomerism present in the starting material. Here trichloroprotonic acid's geometrical isomerism is determined based on the two products obtained after its reaction, or by converting it to for some other compounds of known configuration. Now let us see what is atrope isomerism. Stereoisomerism in biphenyl compounds is denoted by the term atrope isomerism. In case of biphenyls, as the name suggests, there are two phenyl rings which are connected to each other by a single bond. Here we can see two phenyl rings. Here we are talking about two phenyl rings. Here you can observe the alternative double bonds present in both the rings. As there are two phenyl rings, hence we call it as a biphenyl structure. And these two phenyl rings, they are attached to each other through a single bond, and this bond is called as pivotal bond. Okay. Now, although we all know that benzene has got sp2 hybridization and it is a planar structure, yet biphenyl structure is not planar. This, individually speaking, it is planar. This ring is also planar individually. However, when they are attached to each other through this single bond, which is also called as pivotal bond, the two rings, they never stay planar, or they do not tend to stay planar, because when they stay planar, what will happen? The substitution at ortho position of this ring, these two are ortho positions. The substitutions which are attached to the ortho position of this ring and the substituents which are attached to the ortho position of this ring, they will come very close to each other. As a result, there will be steric strain. Okay. Now, as a result, this biphenyl do not tend to remain, or this biphenyl structure, they get oriented in such a way that both of them do not lie in the same plane. However, they tend, if they remain like this, then the angle between these two rings is considered as the dihedral angle. Okay, when we talk about this planar conformation, here it is assumed that both the rings of this biphenyl structure, they are in planar conformation. What will happen? The hydrogens or the substituents at ortho position of both the rings, they will come very close to each other. There will be steric hindrance because of the crowding at ortho position or ortho substitution. In order to reduce this strain, the resulting chiral conformation having a dihedral angle of about 45 degree is obtained, which equilibrates rapidly with its enantiomer by rotation about the connecting single bond or pivotal bond. Now note that a conformation having a 90-degree dihedral angle, that is, one of the ring is considered in a position which is at 90 degree to the other ring, and both the rings are connected through the pivotal carbon-carbon bond. When there is 90-degree dihedral angle, one of the ring lies vertical, whereas the second ring lies parallel. Okay. Now here notice that a conformation having 90-degree dihedral angle is considered achiral, because in case of when we rotate the rings in biphenyls by 90 degree, we can get an axis of symmetry. Okay, when this axis of symmetry is obtained, then the molecule becomes achiral. Okay, and because of because of the presence of this, here we can see the dihedral angle is having a symmetry element, that is, plane of symmetry is here, and as a result molecule becomes achiral. If each of the phenyl rings of a biphenyl has got two different ortho or meta substituents, whereas one of them may be hydrogen, then even the twisted 90-degree dihedral angle conformers, they become chiral. Well, I repeat, if each of the phenyl rings of a biphenyl has got two different ortho or meta substituents, whereas one of them may be hydrogen, then even the twisted 90-degree dihedral angle conformers, they become chiral. If each of the biphenyl ring or each of the phenyl ring of a biphenyl has two different ortho or meta substituents, even the twisted 90-degree dihedral angle conformers, they become chiral. In order to interconvert such conformers with their mirror image, a rotation through the higher energy coplanar form must be made. The ease with which this interconversion occurs will depend on the size of the substituent which is present in the ortho position. Since this group must slide past, now when we rotate, suppose keeping this ring fixed, we want to rotate this, then while rotating, this substitution will, at some orientation, it will come closer to each other, and there may be interaction, or there will be some interaction. So it depends on the nature of substitutions which are present with the two phenyl rings. Now, when we talk about a biphenyl having similar substitutions, however, they are presented at opposite ends, then they can be easily interconverted to each other because of the free rotation about this pivotal bond. As because they are easily interconvertible, it is not easy to resolve them at room temperature. वो एक दूसरे में easily interconvert हो जाएंगे, तो इसको resolve करना बहुत ही difficult हो जाता है. However, if we take a biphenyl structure having two different substitutions at ortho position, in that case, resolving the various isomers at room temperature becomes somewhat difficult. As a result, they can be resolved at room temperature, even though they do undergo racemization easily. However, when we talk about a biphenyl structure like this, what is the difference here? Here we can see a fluoro substitution is here, which is a larger molecule. However, when we talk about nitro group, it is still more bulkier. As a result, the racemization will be very slow and they can be easily resolved at room temperature. So getting converted from, or this rotation about this pivotal bond is not that easy because of the presence of two bulkier groups at both the ortho position. However, one of the two substituents is, if at all it is less bulkier, of course its racemization will take place. However, their resolution is possible at room temperature. They can be resolved at room temperature. However, if both the substituents are too bulky, in that case, there will be racemization which is very, very slow, and the two isomers can be resolved easily. The two 2-dicarboxylic acids on the left below cannot be resolved at room temperature, since the thermal or the kinetic energy is sufficient enough to provide the necessary activation energy for racemization. The two additionally substituted diacids to its right have a higher activation energy for racemization and can be resolved if care is taken to avoid heating them. As a rule, an activation energy barrier of 16 to 19 kilocalorie per mole is required to prevent the spontaneous room temperature racemization of substituted biphenyls. I repeat, as a rule, an activation energy barrier of 16 to 19 kilocalories per mole is required to prevent spontaneous room temperature racemization of substituted biphenyls. Since fluorine, here if we compare this two di-substituted biphenyl, in that case, here since fluorine is smaller than the nitro group, the central compound racemizes more rapidly upon heating than the nitro substitution bearing biphenyl. The conformational isomers that are isolable due to high energy barriers are called as atrope isomers. Conformational isomers that are isolable due to high energy barriers are called as atrope isomers. So, where from this term atrope isomers has come? If we see this term atrope isomers, the term start with A, which means not. Trop means it is derived from the word tropos, meaning turn. Atrop isomers, hence, derived from a Greek word which which means not, and tropos, which means turn. So atrop isomers can be defined as isomers which are obtained as a result of hindered rotation about single bonds, where the steric strain barrier to rotation, or the steric strain barrier to rotation is high enough to allow for the isolation of conformers. That means the steric strain becomes the barrier against rotation or free rotation about the pivotal bond. Hence, isolation of various conformers become easy. Here we can see monosubstituted biphenyl, and here bisubstituted biphenyls. Okay, here it has been observed that this, if we compare these two structures or two atropisomers, then this in case of this biphenyl derivative, the racemization is observed 2 times faster as compared to this biphenyl structure. Coming to the numbering of biphenyl rings, the first ring or the ring towards the left is numbered starting with the pivotal carbon-carbon bond, that is the central carbon-carbon bond. Numbering is continued in an anti-clockwise manner, 1, 2, 3, 4, 5, and 6. Here, the numbering is done in a clockwise manner. Okay, and these two rings, they are oriented in such a way that when A and B, when both this biphenyl ring is associated with a dice substitution at its ortho positions, both the rings having substitution at ortho position, one ring lies on the plane of the paper, whereas it is rotated, so that the distance between the substitution becomes maximum. Conditions for biphenyl compounds to show optical isomerism. When there occurs a plane of symmetry, then the molecule becomes achiral. That we have already discussed earlier. Now here we will see what are the conditions for a biphenyl compound to show optical isomerism. Number one condition is the ortho substituents on phenyl ring must be large enough. When substitutions at ortho position, they are very large or very bulky. The bulky substituents, they restrict the rotation about the sp2 carbon-carbon single bond, and there occurs a lock, and this locks the conformation, making them easy to resolve. Here we can see in this diagram this bulky substitution, they are causing steric hindrance. As a result, the rotation about this carbon-carbon bond become restricted and resolution becomes easier. Condition number 2, resolvable biphenyls must contain different ortho substituents on each ring. These are the 2 rings and these are the 2 substituents. If we can find the plane of symmetry, the molecule becomes achiral. If one or both rings they contain identical ortho substituents, then the biphenyl ring has a plane of symmetry and it makes the molecule achiral. Now let us see the energy profile diagram of biphenyl. Now if we see this structure where both the biphenyl rings, they are lying in the same planar or same plane, and they are having two substitution at its ortho position, same substitution, and in this orientation this biphenyl molecule have maximum strain in the molecule. As a result, its stability becomes minimum and energy is maximum. Now when we rotate this ring by 90 degree, what will happen? This first ring will remain planar, whereas the second ring will become perpendicular. And we get a biphenyl like this, where the strain has been reduced. And we get cissoid, that is 90 degree rotation. After this 90 degree rotation of along this pivotal bond, we'll get this biphenyl orientation, and its energy will be lesser than the cissoid orientation. Now when we rotate it further by another 90 degree, what will happen? It will become again parallel. However, orientation of these two substitution will just become opposite, and we get this type of biphenyl structure, which is called as transoid structure of biphenyl. It has got again strain. However, the strain here is lesser than this type of cissoid strain. Hence, energy level diagram shows it at a lower level of energy content. Now, when this biphenyl ring is twisted further by 90 degree, the orientation or the angle will become 270 degree. Then we will get a structure like this, and here the interaction or here the orientation will be somewhat similar to this. However, as because it is 270 degrees rotation, this adjacent groups will become different or opposite. Here AA was lying on the same side after 90 degree rotation. After 180 degree, B comes to this place, A comes to this place, and after 270 degrees rotation, we get a structure like this, which has got energy content still lesser as compared to this. As it is result, we get this structure, and this upon further rotation by 90 degree, we get total 360 degrees rotation, and we come back to the original cissoid conformation or cissoid orientation. The energy profile diagram of biphenyls can be shown like this. The energy is minimum when the pivotal angle is 90 degree or 270 degree, whereas in the rest three, the energy is comparatively higher. As a result, these three structures are comparatively less stable as compared to these two structures where the pivotal angle is 90 degree or 270 degree. Isomers having similar groups on same side have higher energy than the ones with similar groups on opposite sides. Similar groups on same side, similar groups on opposite side. They have got higher energy, they have got lesser energy. Now let us see what are stereo-selective reactions and what are stereo-specific reaction. To start with, let us see what are stereo-selective reactions. When we talk about stereo-selective reactions, in this reaction, we get multiple products. That is, more than one product is obtained, of which one product is called as a major product and the second may be called as minor product. And both the products are obtained from the same reactant by applying specific condition. Now, by applying different conditions on same reactant, we get different major and minor product. Now, look at this statement carefully. Here, what happens? In a stereoselective reaction, we get multiple products starting from one reactant by applying specific reaction condition. By changing or by applying different conditions on the same reactant, we may get different major and minor products. So in this reaction, we have option to choose the product. Reactant remains the same. However, the product changes. Example, here we have taken the example of Markovnikov's addition reaction. When we talk about Markovnikov's addition reaction, it takes place with unsaturated hydrocarbons, that is alkenes. Alkenes, when added to halogen derivatives, like say for example, here we have taken HBr. The negative, as per Markovnikov's rule, what will happen? Negative part of this addendum will go to that carbon which contains lesser number of hydrogen. Okay, so if we talk about this addendum, the negative part of this HBr is Br minus. Negative part will go to this carbon. This is the carbon-carbon double bond. Addition will take place across this double bond and negative part will go to this carbon, and we will get a product like this where bromine gets attached to this carbon and hydrogen gets attached to this CH2 moiety. As a result, we get a product like this. However, if the same addition reaction takes place in the presence of a peroxide, what will happen? Anti-Markovnikov's rule will be followed. As a result, what will happen? Negative part of the addendum will not go to that carbon which contains lesser number of hydrogen. Rather, hydrogen will go to that carbon which contains lesser number of hydrogen. As a result, we get a product like this. So, starting material in both the reaction is same. However, in this case, the major product is this substitution or this type of addition, whereas as because it is an alkene, the reaction will be addition reaction, and Markovnikov's addition will lead to the production of this product in major quantity, whereas the second product where Br will be attached to this carbon in minor quantity. However, both will be obtained. In anti-Markovnikov's addition, what we will see? The presence of peroxide is there and the nature of the major product is different. The product which was obtained here in minor quantity is obtained here in major quantity. So depending on or by changing some of the reagent, we can change the nature of the major product. Here two conditions are used to get the major and the minor product. However, the starting material remaining the same. Markovnikov's addition of alkene with HBr leading to this major product. However, anti-Markovnikov addition of the alkene with the same hydrogen bromide in the presence of peroxide will lead to a different major product. Now let us see what is stereospecific reaction. Okay, for this reaction, see the term stereospecific reaction. For these reactions, we use different reactants to get different products. Here, starting material 1,3-butadiene or but-1,3-diene. It is made to react with malic acid to get the cis product as a result. However, if at all, instead of malic acid, we take fumaric acid, we get the trans product. So we get only one product for one reactant. In the initial condition, it was not that. In the stereoselective case, it was not like that. However, depending on the reactant, the product is different. So in this reaction, we have option to choose the reactant. If we use the particular reactant or condition to yield, to give exact product that we want, it is called as stereoselective. I repeat, if we use the particular reactant or particular condition to get the exact product which we want, then that reaction is called as stereoselective. The reaction between any two reactants, the outcoming product is selective. Then the reaction is called as stereospecific. I repeat, the reaction between any two reactants leading to the production of two selective products is called as stereospecific reaction. In other words, we can say stereospecific reactions are product selective, whereas stereoselective reactions are reactant selective. I repeat, stereospecific reactions are product selective, whereas stereoselective reactions are always reactant selective. So, as a conclusion, we can say all the stereoselective reactions are stereospecific. However, all stereospecific reactions are not stereoselective. Now let us see some examples of stereoselective and stereospecific reactions. To start with, we have taken addition reaction. Addition reactions with no stereoselectivity. Here we have taken the example of addition of HBr to alkenes. Here addition of HBr to alkene is not stereoselective and it is giving equal product. Here we have taken the alkene and addition of HBr is taking place. We are getting both the things in equal proportion. The syn and the anti form. Both are obtained in equal position. So it is not stereoselective. Now, addition reactions with anti-stereoselectivity. Now let us see. Here the case, addition of bromine is taking place to alkenes leading to stereoselective product. To be specific, it is giving anti-addition. Here we can see this alkene, it is subjected to bromination and we get only anti-product, where bromine and bromine, both the bromines are added in just opposite orientation. Hence we get anti-form, whereas the cis form is not formed, or the syn form is not formed. Here bromine and bromine, they are lying on the same side. This compound is not at all formed, or this addition product is not at all formed. Here we observe only the anti-product and none of the syn product is formed. In other words, the reaction is highly stereoselective for only one stereoisomer over the other. We could go even further and say that because of the complete absence of the syn product, the reaction is stereospecific for the anti-product. Only one type of stereoisomer is formed here. Next is addition reaction with syn stereoselectivity. That means here only syn product will be formed, whereas anti-product is not formed at all. Example is the same alkene subjected to catalytic hydrogenation in the presence of palladium catalyst. Okay, here when this addition takes place, the anti-form is not at all formed, whereas only we get the product syn, where both the hydrogens, they get added up in the same orientation or same side of the molecule. So only syn form is formed in this case. Two hydrogens are added to the same face of the alkene. Hence the reaction can be called as tin stereoselective bearing reaction, or the condition is called as tin stereoselectivity. The product here, here the hydrogenated product bears both the hydrogens which are added to opposite face is not at all formed. As a result, in this example, we can find only syn addition product are formed, whereas anti-product is not at all formed. And again, we can say this is an example of highly stereoselective reaction. There are three key categories of alkenes reaction pathways. First is non-stereoselective mixture of syn versus anti-product, as we have seen in case of HBr addition to alkenes. Reaction that are stereoselective for the anti-product, we saw addition of bromine to alkene, and reaction that are stereoselective for syn product, where we saw the hydrogenation of alkene. The next type of reaction is substitution reaction. To start with, we will take substitution nucleophilic bimolecular reaction, that is SN2 reaction. In SN2 reaction, the nucleophile must approach from opposite side of the molecule in such a way that the leaving group and the nucleophile, they lie opposite to each other. Here we can see this is the starting material and it is subjected to substitution reaction with Br- or bromide ion. When this bromine attacks this alkyl halide, here we can get an intermediate where bromine, the incoming group, and the chlorine, the outgoing group, they lie just opposite to each other, and it is a highly unstable intermediate. Soon this leaving group will move out and the incoming group will get added from the back side. Okay, so reaction proceeds in complete inversion of the configuration. The outgoing group was placed on the front side, whereas the incoming group gets attached from the back side. Here, SN2 reactions are considered as stereospecific as well as stereoselective, as it gives only one product however, with inversion. Now let us see SN1 reaction. In SN1 reaction, intermediate that is formed is a planar structure. Hence, nucleophile can attack from both the sides to give a mixture of both the products or both the possible products. Here we can see this is the structure, planar intermediate structure, which can be attacked from both the sides, either from this side or from this side. If attack takes place from this side, we get a product like this. And if the substituent group, it gets added up from this side, then we get a product like this. And both these resultant product, they represent R isomer and S isomer, to be specific, R enantiomer and S enantiomer specifically. So we can say the resultant products are enantiomers of each other. Hence, we can say SN1 reactions are not stereoselective and they are not stereospecific also. So we can say SN1 reactions are neither stereoselective nor stereospecific, whereas SN2 reactions are stereospecific as well as stereoselective. This is one of the very frequently asked question in various competitive exams regarding SN2 and SN1 reaction. SN2 reactions are stereospecific as well as stereoselective, whereas SN1 reactions are neither stereoselective nor stereospecific. Next, let us see elimination reaction. The difference between SN2 and E2 reaction mechanism is, in case of this E2 reaction, here we can see this bond is, because see, it is elimination reaction. Whenever we talk about elimination reaction always result in the formation of unsaturated bonds, whereas substitution reaction, they are always observed with alkane type of product or saturated type of bonds or sp3 hybridized bonds. Here we can see the OH minus moiety, it attacks the beta hydrogen. This is the beta hydrogen. And when this OH minus attacks this beta hydrogen, what will happen? This shared pair of electron between this carbon and the hydrogen will tend to move towards this. As a result, a new pi bond is formed and the leaving group is lost. That is, the hydrogen is taken out. Okay, and in order to establish this pi bond, this bromine is also taken out and it is considered as the leaving group. Okay, here when the resultant product is formed, we get a double bond. Bromine is taken out in the form of leaving group as Br minus, and this beta hydrogen is taken out by this OH minus to form water molecule. However, when we talk about SN2 reaction, it is this here, this OH minus is acting as the attacking nucleophile. It will attack the molecule in such a way that bromine will leave the place and OH will get attached at its place. Okay, so leaving group is replaced by the nucleophile. The incoming group takes the place of the leaving group. So with this, we come to an end to our this part of our syllabus, that is unit 2 is over.